Thanks again for coming out. Thanks for Duo for hosting this, and you'd be surprised what I would do for free beer and pizza. So, you know, if you didn't know, Dr. Charlie Miller and myself were the ones that originally did this research. It was partially funded by DARPA's Cyber Fast Track initiative before Mudge bailed and went to Google. He was kind enough to help us get cars and get some funding to do automotive stuff. I don't know, a lot of people know Charlie if you know security stuff. He was like the first guy to hack the iPhone, you know, internet sensation, et cetera, et cetera. I was doing mainly like Windows exploitation. I do Windows heap stuff. I reversed all the Windows heaps because I don't know why anyone would do that, but I did. You know, so this presentation really covers first a few things. We realized that there was an amazing amount of work done by some previous individuals that I'll talk about in a second, but they didn't give out any information. And we thought, well, I want to do this, and we want other people to do it, so we should publish all the information.
And DARPA to buy you cars.
And I want anyone to buy me cars. Like, you want to buy me a car and let me hack it? Cool, send me a car. Send it right to Pittsburgh, Pennsylvania. Just put Chris Valasek, Pittsburgh. They all know me there. It'll get to me. But no, we'll talk about the cars that we used, and then we're going to talk about the ECUs in those cars. Those are the electronic control units. Oh, by the way, feel free to shout out any questions, comments as we go on.
So your experience breaking into these is pretty much based on the CAN protocol?
Yeah, a lot of all the control that we did was based off of CAN.
Okay.
And we'll talk about the some standards and protocols that we used within CAN. And then finally, we get rid of the boring stuff. We'll talk about how we actually did CAN message detection.
Is this limited to OD2 port access?
No. As long as you are on the CAN bus, whether you hacked in wirelessly through Bluetooth telematics like OnStar, ODB2, you can physically clip two wires to CAN high and CAN low. It doesn't matter. As long as you're on the CAN network, it's the CAN network, right? And finally, we'll show you how we got the firmware from some of these ECUs, reversed them, did some reprogramming, and actually got persistence on the car as well. What am I talking about when I said people previously did this? There were some academic researchers from the University of Washington and the University of California, San Diego, led by Stephen Savage. I'm a fanboy of their work. Like, they were more thorough than us and achieved more than us, and I love them to death. Their papers were great, but we had one major issue with their papers, is they didn't tell you anything about what they did, which was kind of at least weird for me. You know, I'm not from the academic world at all. I barely got out of college, but I learned how to drink, so that was the most important part, right? But there was no information. They didn't even tell you what car they used. So they didn't even tell you the make and model of the car. They wouldn't give you any information, but they told you, you know, trust us, we hacked this, and I totally believe them. But I thought the point of security research was to disseminate this information among the masses. We have more trained eyes on a problem. Hopefully we can make this whole thing better, right? So we did. And you know, they had a video, honestly, that they showed a car, and they remotely compromised it and then sent some CAN messages to unlock the car, start the engine, unleash the solenoid to put the shifter in gear. And at first I thought, holy shit, these guys are badasses. They stole a car because it's blacked out, right? And I was like, then I found out that it was actually their car, and they just blacked it out because you didn't want to see it. And I was like, well, oh, I thought they were way cooler. They're still really cool, but you know, that's why we wanted to do this. We wanted to get information out there. We wanted to lower the barrier of entry for this research. If you didn't achieve getting funding from DARPA or have a huge research budget, it's really a daunting task to get into this. It takes a lot of money and a lot of time, and we were hoping that by lowering the barrier of entry, other people can start doing the work, and more security researchers, people with an offensive mindset, can start doing this work. And honestly, seriously, who doesn't want DARPA, the government, to buy him a car? It's like my own tax dollars buying me a car. It was amazing, right? We loved it. Car hacking's hard. That's the first thing we realized when we did this. Charlie and I both come from a software reverse engineering and exploitation world, right? So when I want to target, if I want to pop Adobe, I go download it, and I grab Adobe, push it through IDA Pro, start looking for bugs, maybe fuzz test it, whatever. Get in car. ends up being a bit more difficult. We had very specific requirements for these vehicles. So, you know, when John O asked if anyone had parking assist, we wanted to control steering the automobile, right? Well, we didn't know how cars worked because we're both, you know, nerds, right? It's not like we're mechanics. Well, now I am. But we didn't know how the steering wheel would be controlled via computer. So we figured if we got a car that did the parallel parking of itself, right, the parking assist thing, we figure a computer is telling it how to park, so therefore we could figure out how to tell it how to park. And we originally wanted, you know, like we told Mudge that just send us a fleet of Mercedes S55, you know, like 6 or 7 of them will be cool. And they said, buy a reasonably priced car. And that was reasonable to me, so I don't know what their deal is. So we looked for high production cars. And the cars we wanted, luckily I had a friend at an auto dealership, and they found the cars for us, and it was the most hilarious transaction ever in automotive history, because they'd be like, well, what color you want? I don't care. How many miles are you looking for? I don't care. Like, well, I was like, I don't care if it's on fire, as long as it'll park itself, just give me the car. So we had to like buy these cars from people, and they were totally flabbergasted. They were trying to like show us the package. I was like, does it park? They're like, yep. I was like, all right, give me the car. Like, you didn't even ask how much. I was like, I don't care how much it is. I'm not paying for it. Give me a car. So, but it was hard. It took us like a month to find the cars we wanted. The working conditions. This is me working at home in the summer with my super dirty feet on the laptop on the couch, right? It's easy, dude. Hacking from home. I work full-time remote from home. I do actually have a desk, but I like working from the couch because I watch ESPN all day. Working from a car, not so much. There's Unabomber Charlie right there in the automobile. And we would be out there for, you know, 6 or 7 hours at a time, jacked into the car, writing little test programs. In the wintertime, it was freezing. In the summertime, it was boiling hot because it's not like we had the cars running with the AC on or the heat on. We wanted to keep them in a condition, because we didn't know anything about the cars. We wanted to keep them as limited as possible, right? So it's a lot more difficult. Attaching to the target for software is super easy. You could maybe do it poolside, cabana style in Vegas. You know, just 2 handsome bros hacking together in Vegas. Nothing wrong with that. Attaching to a car, not so much for us. Lots of bloody knuckles. This is one of many. So Charlie and I would just, you know, I'm still cut up from working on the car stuff, you know, busting our knuckles off. This is something that we weren't used to. Again, we weren't car guys. We were software hacker guys. Disassembly, at this point in our careers for us, was second nature. You get a binary, you put it through IDA, you start disassembling it, trying to figure out what's going on. You know the architecture. Disassembling a car, a little bit more of a daunting task. You didn't need this to do what I'm going to show you, but we wanted to see where the actual computers were located in the automobile. And for the Toyota dashboard there, it was like 100 steps to get the dash off, because you had to do all these screws, take these things out. It's like disconnect the battery, there's an airbag, and I was like, man, whatever. And I just got a crowbar and just ripped it to shreds. So there's just plastic and stuff everywhere. I'm surprised the airbag didn't blow up in my face, but I'm lucky. Again, debugging for us, second nature, right? You set a breakpoint, try to do something, the application crashes, well, you restart it, you hit your breakpoint, good, it's easy. You can reproduce it over and over and over in a very quick fashion. Debugging a car was harder for us, right? Because we wanted to see when things stopped working sometimes, and we would cut wires. Charlie and I are both very impatient people, so we'd be like, well, let's just cut a whole grip of wires. And as you see, then you have to put them back together. For him being a PhD in math and me being like a computer hacker guy, we really didn't plan a lot of this out too well. Bugs in software, at least for people like me, are good, right? You find a bug, maybe you have a crash, maybe you can find a vulnerability, exploit, you win. Bugs in the car, not so much. There's the trusty Toyota Prius in a way better condition than it is now. That was in South Bend, Indiana, and I'll show you the video that actually blew the car up, and I have a pretty funny story about that whole process. Crashes, right? Those are also good, that you want to get crashes when you're testing software, whether you're use case testing or whether you're testing for security vulnerabilities. Crashes are good for you. The cars, on the other hand, are not so good when they crash. So this is Charlie's garage, and while we were testing the functionality on how to disengage the brakes, we didn't do it on a closed test track because we're not cowards, we're men. And we'd like to, by the way, for the record, take first claim of the first casualty of automobile hacking was us, and it's Charlie's lawn boy. It was completely smashed by his car. He blew the side out of his garage. There's a big gap. There's a couple $1,000 carpenter bill for him, and the poor lawn boy will never mow again. R.I.P. lawn boy, right? Well, let's talk about the cars. First one was a 2010 Ford Escape. Again, we looked for a car that had things like cruise control. The car could pillow park itself. It had backup cameras. Generally a fair amount of tech for the Ford of that era time, and the Escape as well. For example, this is how auto park generally works. This isn't us. This is how the car actually parks itself. So you really are controlling the braking and the gear, right? You go up into the side of a car, and it's going to tell you you're getting close by the audible alerts. And the wheel, you see, turns itself. And, that's the car parking itself. That's how it works. To me, I've blown away how well it works. We would test these cars by parallel parking them a bunch. And I was shocked at how many times it could parallel park itself in a tight spot really well. I had the 2010 Toyota Prius there. It had a lot more tech than the Ford did. It had radar cruise control, right, where if it got close to a car in front of you, it would slow down a bit. It had lane keep assist. If you were going off the lanes of the road, it would recognize and tilt the wheel in. It had a pre-collision system. If you were going too fast and you were about to hit a car in front of you, it would actually apply the brakes for you so you didn't hit the car. And it also had the parking assist. Generally speaking, technologically, the Prius had more computers in it than the Ford did. It was just some guy. So I had to buy this from a guy, not even a dealership, because no one on planet Earth checked every box on the Prius, but this dude did. And he actually found me after we were on the Today Show, and he was like, "Hey, that's my car." And it's like, "You're the one that hacked my car." It's like, "Oh, that's awesome." And he was like, "I have a new Ford. Do you want to buy it?" And I was like, "Nah, I'm cool." But yeah, so that's car. So this guy went, and he had to spend just as much on options for this car as the car had to cost. It's insane, man. The dude, I want to party with this guy because he has to be a crazy man. ECUs, right? Electronic control units. These are the things in the car that really control every aspect. Although they control every aspect, not all of it is done over CAN, but they do mainly control every piece of the car. The general way these things work, right? They take input from sensors, how fast you're going, and do output to actuators, clamp the brakes, right? They're located in various places. In the Prius, it was beneath the glove box. Generally speaking, the engine control module was close to the engine. The braking module was physically close to the master brake cylinder. So it seems like the very, very crucial ones are actually physically located close to where they should be, right? And originally, people were like, "Oh, it's just running QNX, pop it, it has FTP," which is probably true for some infotainment systems, but the regular ECUs in a car are very specific. For example, in the Prius, you had the seat belt control mechanism, and its sole job was to detect, it got a signal if you were about to be in a collision and would pre-tension the seat belt, right, so you didn't smash your face on the windshield. That's all that thing did. So this is not really an operating system that is running on this laptop. It's a real-time operating system that its only task is to look for these messages and act upon them. So these aren't, your run-of-the-mill OS that you're going to see. This is all custom stuff on kind of various custom hardware.
Who wrote that stuff?
Pardon?
Who wrote all that stuff?
Who wrote the code to?
Yeah.
Yeah, no, a lot of them, they run Renaissance chips. Denso is the corporation for Toyota that wrote a bunch of stuff. So they usually, buy from big OEMs for their whole fleet, I would assume.
Some of the infotainment systems are contracted out to
Yeah. It seems like the infotainment systems are even, there's fewer of those manufacturers than there is like the actual ECUs. Like, you have Harman, they're pretty big in BMW and stuff like that I know.
I think Denso has a big office in Detroit. I know a lot of prior Arbor engineers were at Denso doing firmware before that.
Oh man, I got some questions to ask them. Yeah, for sure.
Yeah, a lot of, there's a lot of tier ones, like.
Yeah, okay. I see. Interesting.
Yeah, they're all down this corridor.
Yeah.
They're all here.
I probably should have reached out before I just like scratched my head for 6 months, but.
Are there boutique companies writing this software?
I'm not entirely sure. Unfortunately, we only looked at 2 cars. That's why I want to keep looking at more, because each manufacturer appears to be very, very different. And so we only really can say anything about Ford or Toyota. I guess that.
But they all buy the parts from the same tier ones.
I don't know, probably. The structure was interesting to us, right? So the way these buses work is all the ECUs are linked up, and they can all hear everything each other says, and they all can send messages out. There's no authentication, there's no authorization, and there's no encryption, right? The way these things work is they periodically spit messages out, and the ones that figure out what messages they want consume them. So just imagine this room, everyone shouting whatever command they want the whole time, and if that's a command you listen to, you follow that rule. So that's something to note, that this architecture was designed in, I think, '83 by Bosch, the CAN bus, and they don't have a crystal ball. They didn't know that there's going to be external input to all these things in 2014, So it's one of those things that just happens. There's architecture and technology developed before there was security. That's just kind of how it goes.
So they're not using any security protocol. Does the CAN bus support any kind of?
Natively, it does not support like authorization or authentication. There's some stuff I'll talk about for getting privileged access on these ECUs that do have some kind of authentication, but we'll show you how to beat that up in a little bit. So this is a Ford connector here.
I mean, if you really want to get into this other modes, there is security there. If you want to do flashing, if you want to do engineering modes.
Yeah, I'll show you about that.
You got to get through this.
Yeah, we'll get to that. So there's like a ECU, right? That's generally what we're looking for. The circuit board, it has stuff covering it. I assume this epoxy type stuff is for weathering, right? So like rain. Yeah, so but the cool thing is that, right, you go up and get fingernail polish remover, and it just comes right off, so you can see the chips and what they are. We look for things like that, right? Debugging headers. Those are the type of things that we're looking for on these boards. Quick overview of CAN. This is quick and dirty. But we were interested in the application. We're not talking about checksums and things like that. Generally, we're bits and bytes people. I want bytes so I can look at them. The CAN IDs are either 11-bit standard or 29-bit extended. Both of our cars only sent 11-bit messages. It appears that most passenger vehicles use 11-bit CAN messaging. Things like heavy machinery, big rigs, earth movers tend to use 29-bit.
Usually what you'll find is the powertrain people tend to be 11, the vehicle side people tend to be 29.
I see. Yeah, I mean, in all our vehicles, everything was 11 bits on there. The data length is, in the application layer, can be 0 to 8 bytes. The maximum you can send is 8 bytes. I'll kind of show you how there's a caveat to that using certain protocols and standards. The nice thing is the ID field is used as a priority, right? So ID 0 is the highest priority. That's the most important message on the bus. They use it for arbitration, right? So if there's anything confusing on the bus and they need to arbitrate, the lowest ID wins. So nice CAN DOS, right, is send a bunch of messages with ID 0 a bunch, and you can shut down a CAN bus. As I said before, they're broadcast in nature. And that means it just spits it out in the network, and whatever's there hears it. So you don't have to be, say, the steering ECU to send steering packets. You just have to be on the CAN bus. As long as you understand the format, which is usually proprietary, and the ID for steering, you can say, hey, turn the wheel at this angle, right? And again, that comes down to really something that was just designed a long time ago. So this is a format that I developed on a plane because I didn't have the internet and I couldn't figure out how to use string tokenizers properly. But I spent so much time at ISS writing signatures for our IPS device that I could write a state machine that parsed single bytes. And that's why I invented this format here. Very human readable, very API consumable. But basically you have IDs. We broke them into two parts, ID high, ID low, the length, and then the data. Toyota ended up having the last byte in the data usually be a checksum. So this plus this plus this plus this plus this plus this cut off at byte alignment, checksum. So the messages would not work unless you set the checksum. I think we all know that you can just set the checksum or whatever. It's pretty easy. So this is a format we invented. If you ever look at the code or the tools, anything we use, this is our format. Diagnostic messages are a bit different, right? Those normal messages I was talking about, the ECUs are constantly spitting them out, just regurgitating them onto the network. These diagnostic messages, on the other hand, are usually sent out by a mechanics tool or something like OnStar. They don't happen really on a periodic basis. They'll happen when issued. And the way they really work is they have an ID, and it sends it out. And that ID is really going to a specific ECU. Before I said there was really no addressing to this. This kind of is sort of addressing. ECU, you know, the ABS ECU in the Ford Escape is ID 0760. And the response coming back is always going to be 8 more. So the response is 768, and that's how you communicate diagnostically.
An assigned number authority somewhere?
No, it's just however they want to do it. Each manufacturer is different. I think there's a list of standards that for engines and for emissions and things like that.
OBD stuff is mandated.
So you'll see that. But the thing is, even though the ODB stuff is standard, I'll talk about ISO later. It's like the first 3 bytes are standardized, and then the other ones can be proprietary. So Fords are going to be different than Toyotas, that are going to be different than GMs and stuff like that. Standards and protocols. Let's get through this boring stuff because we wrote libraries for this stuff, and if you want to actually learn it, you can read the docs. Otherwise, just use our library and it'll work like unicorn magic. The first one is ISO-TP. Before, when I said they can send 8 bytes at a time, that's true. One message can be a maximum of 8 bytes. But if you want to, say, update a firmware, you're going to need to send more than 8 bytes, obviously. So the way they do this is they take the first byte of data and have kind of an indicator in the first nibble. And you know, it can be, I'm a color by numbers guy, so this is probably easier for me. A single frame, so this one is saying, hey, I have 3 bytes, right? 14FF00. If you want a multiple frame, the first nibble is going to be 1 saying, hey, there's multiple frames coming for you. The next 3 nibbles are going to be the size, 82 hex, and then it starts sending the data. The 30 is a response, just an ACK, really, like, hey, I got that, let's go, let's start sending the data, and then you send it out. So this ISO-TP, when you go to your dealership or whatever, and they do a firmware update ever can, this is normally how they're doing it. The second ISOs are 14229 and 14230. They really leverage ISO-TP to send multiple bytes of data to a single ECU, but they specify services that you can run. Just think of it like services on a computer. Here's the general recommendations for, you know, a certain service. They don't have to implement them. This is just recommendations that if you're going to, we recommend doing it this way. I'll tell you for a fact, it seems like a lot of people just ignore this and do it proprietary. A diagnostic session control, right? The first thing a mechanics tool usually does, right, is say, do a diagnostic session control. ISO-TP, 2 bytes. 10 is diagnostic session control. 3 is the type of diagnostic session. And then if it's a success, it's always 40 more than the command. So 50 is good. If it's not 50, that means something went awry, right? This is the one most people are familiar with, security access. So if you want to do a privileged operation on the ECU, for example, you're going to want to get some sort of an authority to do this. And we'll talk about this later. But generally, it's the same thing, right? 2 bytes, there's a security session. The type of security session sends you a seed back. It does some magic. You send you send the challenge response, and 40 more, 02, we're all good. We'll go over this more here in a little bit. But there's a bunch of other services. There's like input and output control. This is basically saying, hey, I want to test the physical nature. You're going to basically supply the sensor input for the ECU. So you're saying, pretend the sensor is telling you to clamp the right front brake caliper. These are ways that mechanics can test pieces of things without physically getting down in there. If it works over the CAN bus, that means that, you know, the functionality's there. Maybe it's a different wiring somewhere else for a switch or something like that, right? Very good for monitoring how these work. There's a bunch of interesting ones. Read memory by address, write memory by address, request download, request upload. When we saw these, Charlie and I figured, project's done, man. Easy. And read the firmware off. I'm a reverse engineer. I'll figure that out. We'll load it back up. Computers pop. Done. Easy. DARPA's going to give us our money. Internet famous. Spike the mic. Move on. None of these were implemented by any of our cars. And it's very commonplace not to implement these for the very reasons that I just talked about, right? You don't want people just taking the code off your ECU and dumping it right back on there.
Powertrain, government mandate, you got to do this.
Maybe not these ones.
For engine control.
And not for our cars. I can assure you, definitely not for our cars.
Government mandates primarily around emissions.
Yes, anything mission control.
Yeah, but this is grabbing the firmware off the thing. You can grab data values. You're not grabbing the firmware though. If I could have grabbed the firmware, trust me, I definitely would have used this method instead of the ones I'll talk about. So we went through Canada standards and all the services that could be used and stuff. Let's talk about some tools we used. I actually brought this with me. This is an ECOM cable. There's a company called eControls. They're super nice people. They're like support and engineers actually contacted us. And basically has a nice Windows API to do reading and writing of the CAN bus. So it was nice that, I'm really familiar with Windows. Comes in kind of two models. The first model that we bought cost $1,200 and it has 3 exposed wires on it because we figured that's what we need. And there was another model that was like ODB1 or whatever the circular one is that has 9 pins. That was like $200. And we're like, well, DARPA bucks, whatever. Let's get the expensive one first and make sure that we can do what we do. Well, Charlie got that one. He's like, I don't know, this doesn't work. And I was like, screw it. I'm buying one of the $200 ones, and I realized they had a wiring diagram. I was like, oh, there's CAN high, and there's CAN low, and there's the ground. So what do? You buy the $200 one, cut the end off of it. You buy one of these things, an ODB2 shell for 25 cents, and you hook some wires up to it, and you get a little thing that looks like this. And you save yourself about $1,000 per unit. And being that we both had 4 of these, it was very beneficial to save $1,000 a unit for us. So in our paper, we give you very detailed descriptions and pictures on how to make these. I got one here. After we're done, if you want to see it, I'll show it to you. Super easy. Electricity to me is magic. Like, I don't understand that. I'm a software guy. I don't know anything about electricity. And I was able to create one of these. So I think everyone should be cool. Another thing we use, especially for the Toyota, is a thing called a J2534 pass-through device. When you go to a dealership, they basically hook one of these up, and this machine hooks to your computer, and then they use mechanic software to pass messages back and forth, update. The cool thing is, do I have the slide in there? No. You just buy, what we did is bought an ODB2 splitter, just wires that split it out into a Y, and we would use this guy to, say, update a firmware. And then we would have our sniffer on the other side. Since it's broadcast, we saw the traffic, and you can use that to figure out how they work, right? A little bit of network reverse engineering. Speaking of software, we hand-rolled our own. And there's a company called Vector out there, which most automotive people are familiar with. They look like they make some amazing product. And I've actually seen it, and it's just as amazing as I thought it would be. It is very, very pricey. Pricey enough where we didn't build it in and definitely weren't going to buy it. So like any good hackers, what we did is wrote our own, right? And the first thing we wrote was a thing called EcomCat. If you're familiar with Netcat, you can probably understand why we named it this, because we love cats. Yeah. It's our little Swiss Army knife, right? This thing could read from the CAN bus. It could write to the CAN bus. It could read out onto disk from a CAN bus, take a capture from disk right on the CAN bus, message filtering, all written in C, runs really quick. This is what we use to kind of sniff network traffic, right? But we realized that it wasn't conducive to running different tests. Say we wanted to send one message for a little bit and then like stop and then think about it and send a different one. So what do? Bind it to Python, right? So we have EcomCat API. Python bindings to wrap all the C code, so you can say stuff like send a message and give it text. String parsing, much easier in Python than it is in C, right? You can do it prototyping really fast. It abstracts all the ISOs and standards I talk about. So instead of doing all the bits and bytes for the ISOs, you can do Toyota_security access. And you don't need to worry about how it works, it just works, right? And lastly, I kind of took over this thing and I called it PYECom. There was a lot of different weird things with the Toyota as opposed to the Ford. They did a lot more proprietary-based stuff that I reversed out. So I figured if I'm going to reverse out, I don't want someone to do that again. So I'll write this library, and you can just use it and not worry. So how's all this stuff work? You want to write to the CAN bus. Before it was like, buy this thing, do all this work, maybe get vector or whatever, but we wrote this Python library. You stick that thing in USB, connect it to ODB2, open the device. There's a format that we invented, right? You can change all these bytes, do whatever, write. So 3 lines of Python, we made it so you could do this work. We want people to rapid prototype little programs they write. So there's what you can do. You can write message, you can write them for file, you can read them. We have a bunch of stuff. We released all this code too, so it's free for everyone. Go grab it, augment it, tell me where we messed up, whatever. We just want people to use it. All right, so I hope I didn't bore too many people with all that stuff. Now we can talk about the cool stuff, how we made the car do, bad things. But I first want to mention that there are limitations, at least now for the cars we had that were made in 2010 and probably designed in 2008. Not everything happened over CAN. And we were under this assumption when we got the car, it would all be on the network. You'll even see things like we would see on the CAN network the angle of the acceleration pedal. You could see it go higher to lower as you depressed it and released it. And I was like, sweet, put it to high, I'll play that in the network, and the car will zoom forward, right? It's not the case. There's kind of reporters, sensors just telling you what's up, and there's consumers of that information. If there's really no consumer of that information, then it doesn't really mean anything. I'm sure there's something that's messed up in the car, but it didn't physically control the automobile. The Ford Escape, for example, had electronic throttle, throttle by wire, but the sensors went directly to the ECU, 4 wires from the pedal to the ECU. So it never was broadcasting the network. You could physically manipulate these, but it'd be the same effect as being there to press the pedal. You couldn't do it, say, if you remotely popped the car. And then we had a problem of original versus forged messages. You'll see a video later where we changed the speedometer, right? Although we're telling the speedometer that it's going 20 when it's going 0, in reality, the speed sensors are still telling the car it's going 0, so you kind of have to compete with these. And the way we competed with them was just be obnoxious. We shouted longer and louder, right? It was sending the message 10 times a second, we'll send it 10,000 times a second, so we'll win. So you have to kind of compete with the messages that are always on the network because they're constantly being spit out. And lastly, there were safety features. You'll see us turn the steering wheel of the Prius. It wasn't as simple as figuring out the steering wheel angle and saying turn it to an angle we want. It actually required you to be in reverse, in intelligent park assist mode, and going less than 5 miles an hour. Luckily, where do you think it got all this information? The CAN bus. So we could forge these things, but it did take us a while to figure out what the limitations were for these things. And luckily, we used a bit of logic, and and by logic I mean just bashed our head against the keyboard for 6 months.
Here's an electricity question.
Oh,
which I don't even understand.
magic.
Things like Ethernet. Do you know what kind of collision avoidance or collision detection they use on the CAN bus?
Oh yeah.
Or simultaneously transmitted messages.
Whoa. Yeah.
If something tries to start transmitting and something else is already transmitting a higher priority, it'll back off.
Okay.
Basically,
So you might be able to blast higher priority messages to beat the originals?
Yeah, but the higher priority ones are going to be different than the originals, right?
What happens, for example, the signal, the stereo angle signal, it's tied to the ID, the address. So you can't use a higher priority one because it's using for that exact value address
Yeah.
to know what the
Yeah, like the steering ID in the Prius is 25. I have all these memorized, which is almost
how this
despicable.
actually works. So the reason lower is higher priority is everyone has pull-up resistors on the bus. So 1 is passive and 0 is active. If at any time you're watching what you transmit, if at any time you see yourself transmit a 1 and there's a 0 on the bus, you just lost.
Yep.
So you back off.
See, that's electricity that we don't understand.
That's how.
I was going to say,
It's like, oh, sounds good.
it was going to be FM. Effing magic. All right. So normal can injection, when I say normal can injection, these are not diagnostic packets. What we did here, as opposed to what the guys, the researchers at Washington and California, San Diego did, was we examined messages that actually were naturally occurring on the CAN bus. These were always being spit out. And we just forged them and sent them faster, and we won, and the car did stuff. So how do these work, right? For example, we decoded, when I was doing IPS, IDS at ISS Force, we call this a decode. We figured out the proprietary message scheme. What do you know? For the CAN ID 0201 and a Ford, these are 2 bytes equate to the speed in RPM. Do some math. Charlie does math. He has a PhD in math. I let him do all the math. And the example, you can get speed in RPMs, right? What do you want to do? The nice thing is you can copy this message, and this should work for a Ford Escape, and you can set the speed and RPM to values that you want, right? You literally can copy and paste that Python code, use an ECOM cable, use our software, and this will do it. I'm not playing Charlie's because he made the video wrong. It plays upside down. So screw it. Virtual Charlie, thanks for messing that up. I'll show you the Prius. So this is me.
Okay, we're obviously in park. We're not going anywhere.
I don't know why I did that because it always says idiot.
We're going 20 miles per hour.
Listen to the beeping and I'll tell you something. So I found out what the speed message was, and a consumer of that speed message was the display, right? I figured out what to set the speed as. I did 20. But you also heard the beep, right? You know what that is? It says put your safety belt on, right? So here you have to think about this. When you're sending messages out on this broadcast network, not only are you changing it for the display, but anything that was dependent on doing something with speed was notified that you were going 20. That's why it said, hey, put your seatbelt on, because it thought I was going 20 miles an hour, because that beep doesn't come on unless you're going above 5, right? So it doesn't annoy you. So not only when you send these type of messages that you're changing one thing, but there's a lot of collateral damage that happens from anything that's listening for that ID in the messages that you're forging.
So can you, like, say, set the miles per hour to be, like, say, 120 to hit, like, that passes the governor, so the governor shuts the engine off?
I never tried that, but I don't think that happened. So I'll show you something weird we did with the speed, but I don't know if that would work.
I like how you just use it in your driveway for safety purposes.
Oh, you're gonna see some real safe stuff here in a little bit. Yeah, if you watch the academics video, they have like helmets on a closed runway and gloves, and it's like Charlie and I on our cell phones, like Hello Kitty dice hanging. Braking. So how do we brake? I found out that the Toyota had a pre-collision system. I didn't want to be dependent on diagnostic messages, right? Because generally speaking, there's a fairly simple way programmatically to stop these. You don't let them happen when the car's running. But for braking for the Toyota, if you have a pre-collision system, right? There's a millimeter wave sensor on the front. If you're going fast, it detects that you're going to come up on something too fast. It will activate the brakes. Here's the decode. There's the message that you can send. Oh, what do you know? There's some easy Python code. You can copy and paste that guy and completely immobilize a Prius. You might ask, Chris, how did you figure out how this car would automatically brake itself? And what you do, real easy, you go to Home Depot, buy yourself 4 15-gallon garbage cans, and you stack them up by your neighbor's house. Then you back your car up 70 or 80 times and go 60 through the cans until the cars finally stop before you hit the cans the one time. And then you sniff the network and do that. Real safe, real easy. Do it on city streets. Police don't mind. They're cool with it. And here's us doing this at our closed test track in South Bend, Indiana, behind an abandoned Walmart. I think we're going about 40 or something here, and it's only one message. So as long as we replay this message a bunch, the car stops itself. And at least for the Prius, when you're stopping, it's kind of a pressure amount, right? Because they want to slow you down. They're not going to clamp them. They're going to slowly clamp. So what I did is just do 100%. the Prius has that booming 1.4 four-banger in it. So even if you pressed the acceleration pedal the whole way down and the gasoline engine on, the car wouldn't move, right? Because the brakes were clamped and it couldn't move. So this not only brakes the car, but completely immobilizes it as long as you play this message on the network. Steering. So this I think was our major contribution. The academic guys did a more thorough job than I think we did. But at the time, they didn't have a car that had steering, right? It's just, for them, it was direct linkage. You physically make things twist and it turns the wheels of the car. The nice thing for the Toyota, since it had the parking assist, it had a servo mechanism on it. And this servo mechanism would physically turn the wheel for you, right? So after a while, we figured out that this ID, 0266, was for the servo mechanism. And there were certain bytes in here that told you if it was parking itself. But you still had to be in reverse and going less than 5 miles an hour, because it would only parallel park in reverse and stop. Well, after we figured that out, this is the code to do that, by the way. You can do some stuff. This data file is also available for download. What we did is I wanted to figure out if I could flood the network with speed packets. And, I talked before when the seatbelt dinger was on that something happened, so I figured, what can I do? And I looked at the speed packet for a while, and then Fuzzer Chris came to mind. And I saw what the speed was, and it was 2 bytes. And I was like, well, FF. And I just kept, and I got 2 ECOM cables at that point, and I flooded the network with one, telling it was going the speed of light. And we sent an invalid speed message so quickly that ECUs that were dependent for steering decided to go offline for a little bit. So we'd knock these ECUs offline. The moment that happened, we'd then send the packets like, hey, turn the steering wheel the whole way to the left. And you'll see the steering wheel do counterclockwise rotation here. And it's not smooth because, right, it's originally saying, I'm cool. Then it's like, oh, shit, I don't know what's going on. And it's like, turn left. It's like, all right. So it's not really fluid for that reason, that you're kind of tricking it into thinking it's in a state that it shouldn't be in. And this is me trying to kill Charlie, by the way. He makes a mistake here of taking his hand off the wheel for 2 seconds. Idiot move. And I don't know if you can hear it beep right before it turns. That's the ECU going offline. There was a message that came up, right? And this is the wheel turning. Pretty drastic turn. Also, that shrubbery, since it was an old Walmart, just had a steel I-beam in it. So we came like this close to hitting it. But the neat thing to know about this, too, is since it was a servo mechanism, the wheel just wasn't turning gently. It literally ripped it out of your hands because you were saying do it full force, right? So if you weren't paying attention, like he wasn't at one point, it just turns.
Could you resist the servo if you had it?
If you had like a death grip on it, so like we freaked Andy Greenberg from Fours out enough when we finally did this test. He was like white knuckle teeth grit, and like it kind of jerked on him, but he wouldn't let it go. But if you hit someone that they were like, riding dirty, listening to music, it totally went out of hands.
So that steering though, it's a kind of traditional power steering, hydraulic power steering.
Traditional power steering, it just has a servo mechanism that'll turn when you're in the parking mode for you.
And they're not even hydraulic anymore, are they? I think they're fully electric.
Yeah.
Yeah, the newer ones, like, my Taurus is all
Yeah.
electric now.
Yeah. So I want to check out like the new.
It's even electric to where if you hold the wheel straight, it'll steer, it'll correct its steering.
Yeah.
Like with the wheel straight.
So that I want to check out like the new Infiniti Q50, right? Because it's completely drive-by-wire. There's no linkage in the car. It's only sensors, right? So I want to check that out. So if anyone wants to give me Infiniti, just hook it up, man.
What color?
Doesn't matter. How many miles? Doesn't matter. Acceleration, right, was another one of our goals. This is a bit of a different process, and we took a different method. In the Prius, you could, it was accelerate by wire, but the sensors would send messages to the hybrid ECU, since the car runs on gasoline and an electric motor, and it would determine where to do things. But I found, and just to prove that you could do this another way, instead of doing this through ODB2, I found the ECU, and I just put 2 wire clips on it, 2 little alligator clips, and in between the bus, and I could send messages saying, hey, we're to the floor, right? And the car would accelerate itself if the internal combustion engine was activated. The moment it activated, you kind of accelerated. We did this because it was a bit segmented. If you owned a car, you would own this ECU anyway. But we wanted to show that, yeah, that you could also just jack in, right? Like, so if there's any exposed CAN wires on a car, you can just put 2 little alligator clips. I know that the cool thing, well, cool from my perspective, is like I think on new Bimmers, the windows, the like side view mirrors will tilt down when you go in reverse, right? So they're probably on the CAN network. So you could literally like wire right behind the mirror, little device in there, and do kind of. Yeah. So you could do this stuff externally from outside of the car without having to physically enter the automobile. So you can attack an automobile locally without having physical entry to the cabin. There's an API, one message. This means put it to the floor, Chris. Warning, I will tell you a story after this. This can harm your car. If you have a Prius, don't do this test. Other ones, you'll be cool. It'll be weird, but like your car will physically function. You can try to see the speedometer increase, but I try to lift my leg up, and you'll see the car accelerate more. It's hard to show this when it's just you and your buddy Charlie messing around. So I get the internal combustion engine engaged, right? Because it'll go after like 20 miles an hour in the Prius, and then I lift my leg up, and the car continues to accelerate, right? And we think this is funny for some reason. The RPMs are still spiked. My foot is off the gas. Cannot stop the car as well. And then finally, I accidentally kicked the cable out and it stopped. And if we would have went 4 seconds later, you would have heard pop. I was supposed to drive home from South Bend, Indiana, back to Pittsburgh this day. Well, we heard pop, and I was like, Charlie, don't worry, man. This thing will cool down. We waited out there 10 minutes and joked around. It still wouldn't start. And I was like, well, what do? You just go to the bar and have a drink. So we went and had 1 beer, and then got a coffee, and then came back, and it still wouldn't start. So finally, I called a flatbed tow truck, and I was like, tow this thing out of here, man. They're like, where? I was like, there's a Toyota dealership down the road. And they weren't even open. It was Sunday. I was like, just ship it there. I'll figure this out later. And I drove home. And the next day, I get a...
You texted me, and you're like, I'm in South Bend.
Yeah, I texted John O. I don't know what to... I live here now. This is my life. Like, I just live in a strip mall in South Bend, just begging for change. But I get home, and the next day I get a phone call, and I see it's like from South Bend, Indiana. I was like, hi, this is Chris Valasek, and hey, this is from blah, 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 South Bend Toyota. And they put a mechanic on. He's like, dude, what's the deal with your car? And, I was like, oh, man, I don't know, dude. Like, it's a long story. Can you just figure out what's wrong? I'm not a mechanic. I don't know. I was like, shit won't start. And that's all the advice I had to give him. Well, like a week passes. I didn't get no phone call. And they finally call me back. And they're like, yeah, we got guys from Toyota headquarters coming in here. We don't know what's up. No. And then like another week passes. And like, so I don't have the car for 2 weeks. And finally, they call me back, and they're like, Toyota wants us to put this thing back together again. And I was like, you're not putting Humpty Dumpty back together again. I assure you, it is busted. And finally, the guy's like, well, I don't know, we'll try one last ditch effort. It's like, do whatever you have to do. Like, my mechanic's bill at this point is like $2,000 for I don't know what's wrong with it yet. Thanks, Uncle Mudge, for the DARPA bucks, because I didn't want to pay that bill. They finally figure out that we blew up the inverter. Just since we were clipped directly into CAN, we were bypassing all the safety mechanisms and regulators that happen in the ECU that usually say, oh, you're floored, you're going to redline, I'm not going to give it any more gas. Well, since we were clipped directly into the CAN line, like I said, bypassed all the safety mechanisms, and it blew up the inverter. It cost $4,000 just for the inverter and some minor fixes. I think the bill was like $5,000 to get this fixed. We actually have, Charlie and I have it signed. I have it home in my garage. We're going to send it to Mudge as a trophy for thanking him to do the work. But the moral of the story is not only can you physically potentially harm a passenger in the car, if someone did this to my car and you had to pay $5 grand, I'd be pretty peeved about it, honestly. House cup me, John O. House cup! Yeah. So those were normal messages. Those were messages that we saw that were actively being sent out by ECUs, and we copied them and set them faster and changed the values to whatever we wanted to do. These are diagnostic messages. These are not normally occurring. They really only occur when a mechanic's trying to do something. A lot of the times, there's privileged access that needs. You want to bleed the brakes of the car, you have to get privileged access to do that, right? And there's a challenge response system that the ECU and the mechanics software have to put it in a certain state. Here's one example from Ford, which was funny. So we got the firmware.
Special delivery.
Thanks, dog. We got the firmware for the parking assist module from the Ford. And we realized after doing security access with the parking assist module, the random seed is supposed to be random at least every time you start the car. Was always 112233. Always. So for this one, we didn't need to defeat security access because we just replay CBBF91. We don't need to know the keys. We don't need to know the algorithm, whatever. After we got the firmware, we saw there was actually a branch instruction to a place where they generated random numbers. So our conclusion is they may have left debugging code in there accidentally and didn't take it out.
They left the back door in.
Or the NSA'd it. It's the NSA. Yeah. So things like that happen. But what if there isn't, an anomaly like this? What do you do? Well, we're software reverse engineers, and all this software is mechanics software that looks like it's written in the 1990s, right? This was the easiest part of the project for me, because I knew this is my bread and butter. This is what I did for a living, right? So after a while, we figured out what DLLs they used, and lo and behold, you figure out where they actually store their secret keys. Here's all the keys for Ford, Lincoln, Mercury. They had some cool ones. They had ASCII ones, which was funny. They had some Bosch. They had Jesus, but not God. I think Conti is a person. Someone told me that. There's a dude named, his last name I think is Conti at Ford. Mazda, obviously. But I mean, this isn't really shocking stuff. So if you want to do security privilege operations in Fords, we published all this stuff. Honestly though, this is it's security through obscurity, right? Because if the keys exist in a binary that I can grab or on the ECU, there's no key exchange. So they have to exist in both places for the algorithm to work. So if you have access, you pop those. You want some Toyota Lexus Scions? There you go. I actually found the first one. It's the super, I forget what the cipher is. I think it's called XOR of 2 bytes. And I actually figured this out just by getting a value, and I was like 2 bytes, and then I just XOR'd it through a loop until I got the correct value, and it worked. But then I later, reverse engineered all the stuff and figured it out. There's a few more keys that we published later, but generally speaking, you can get those keys from the mechanics software easy breezy. If you do reverse engineering for a living, it really shouldn't take you more than a day to get all that stuff out. What can we do with these diagnostic messages? For a lot of them, we honestly didn't need security access. They just kind of worked as long as we figured out what they were. How do we figure out what they were? The mechanics software has these tests in them, so the mechanics can do them, right? So we just set up our sniffer, run the test, see what bytes happened, and there you go. So you can kill the engine of the Ford, right? And Charlie brought his kid with this one. I don't think his wife is too happy about it. And he says the cutest thing ever, too. So the car won't start.
Did you kill the engine? Yeah.
So as long as you play this message, you can't turn the car back on. You can turn it off, try to turn it back on. Doesn't work, right? What else can you do? I keep my lights on auto all the time just because I'm forgetful. I've ruined a battery just for getting to turn my lights off. It's the way it goes. In the Toyota, you can turn the lights on and off with diagnostic message.
In auto mode, we can turn them on, and we can also turn them off.
So if it's in auto mode, you can determine when they go on and off. Great test for mechanics to see if the physical bulbs are working without actually taking them out of there or whatever. The Ford did special security access, and I think it's called the Smart Junction Box. Once you put in security access to be in reprogramming mode, everything kind of shuts down in the car, which is kind of crazy.
I don't know about the DOS, the Smart Junction Box.
Because you need the bandwidth.
So I lose my lights immediately.
Yeah, so they're going to want all the bandwidth for the firmware coming over.
Stuff, so the radio.
Yeah, the tail lights, there's no brakes on the tail lights. The solenoid won't unlock.
No matter what you do, brakes don't work, or the brakes work, but the brake lights don't work. Then you can't get out of park. You're stuck in park.
Is my DOS in the bus?
Yeah.
CAN bus?
What's that?
DOS in the CAN bus?
No, you're just putting the one piece of, the one ECU into a reprogramming mode. And from that, it kind of shuts everything down and is waiting for firmware. But
When you do a reprogramming session, the very first thing you do, you should tell everybody shut off.
Yeah.
But that's before you do the reprogramming.
yeah.
Additional input.
One of the more benign and funnier ones was the horn. I think this is funny to me because I always thought a horn was two pieces of metal. When pushing it, you complete a circuit, and that's the horn. But like, you know, this also can be tested over the CAN bus, and this is us messing with Andy Greenberg.
Oh my god.
And you can't do anything about it. The nice thing is, even when you turn the car off, the CAN bus stays active for a couple minutes. So as long as you replay this packet, the car's off and the horn is still blasting. So my neighbors hate me because I would just like hit it and then walk back in my house and get a cup of coffee, and the horn would be blowing off, you know, for a minute and a half.
In a lot of vehicles, if the CAN bus is active, nothing goes to sleep.
Yeah. Well, I don't think some things broadcast messages anymore.
No. At least in the GM and Chryslers, the
Yeah.
entire vehicle wakes up when you get a CAN message out there.
I see.
So be careful.
So you can end up.
Yeah.
flattening your back.
So that's not how the Toyota worked for sure, because you could send CAN messages and the car, you know, I'd go up first thing in the morning and try CAN messages and nothing would happen. The seat belts, right? We could actually pre-tension the seat belts with a diagnostic message that to say, you know, test these to make sure they work when you get in an accident. Again, pretty benign. But tell them to fight it, Charlie. It's more annoying than it is anything, right? But again, this seatbelt motor and ECU is just a thing that hears a message and it just, you know, gives voltage to a motor that pulls the seatbelt. Like, so it was one of those things that I thought was so simplistic, but at the same time, it's also on this automotive network as well, right? Locking and unlocking the doors is probably pretty common for every diagnostic tool. The thing to note, I guess, is if you did have a remote exploit and wanted to thief some cars, I think this would be a portion of the exploit.
Message to unlock all the doors.
And that did all 4 doors in the hatch. So you can lock and unlock the doors. This one I put in here, it's a parlor trick for sure. But the response I got was better than the actual thing. We have a 1/4 tank of gas, right? Yeah, and the gas goes full. I want to get like a remote USB dongle and like put it in my buddy's car that has a Prius. He always thinks he has a full tank of gas. And then laugh at him when he breaks down. The best question we got after DEF CON is someone earnestly came up and was like, so, you never run out of gas? And I was like, I single-handedly solved the energy crisis. Where's my Nobel Prize? And like, I felt bad because afterwards I think they realized how flawed that statement was. But I was just like, I didn't know if I was getting trolled or not. Oh yes, for the record, you will not always have gas if you play that message. The one that was scariest to me, because I'm the driver, was disabling the brakes. This did have some safety stipulations that you did need to be going less than something like 8 miles an hour. You had to be going relatively slow. If you sped up, the brakes would work again until you slowed down. Charlie was testing this functionality on our closed test track outside of his house in St. Louis. And he was testing it all day, and he finally figured out exactly how it worked, that there was limitations on how fast he could be going. So the way he wrecked through his garage is he was coming home after testing, still playing the message to bleed the brakes. And he got to his garage, and he realized, oh shit, my brakes don't work. I have to hit the gas to speed up. The moment he hit the gas, he realized that, you know, to the left of him was his wife's car. To the right of him was his house, but straight ahead was the garage. He was like, screw it, boom, and then went right through the garage. And that's how, on our closed test track, obviously. That's how this happened. But when do you want to stop? When you're starting to slow down. You know, my joke in the Forbes video was, you know, the orphanage lets out and you're coming across, you're just going to run them all over. Very distasteful, Chris. I agree. It makes this weird growl sound too when you press the brakes. We go over the curb. By the way, I try to brake with my left foot that I've never done in my life. I just started to panic when it wouldn't work and I started doing anything. The only reason we stopped is I kicked out the plug. Otherwise, we would roll right on the train tracks there in South Bend. But yeah, you can make the brakes cease to work. And I think things like this is kind of an easy fix, right? If you have ever been in drive and the car's been on, this shouldn't work. So, it's one of those things where you're developing this for people to test the car. You're probably not a lot of security consideration put into these things as they're being developed. I'm not trying to point and laugh at someone. It's just that security, not everyone is Microsoft and has a concrete SDL when they're writing all their software. It's just the nature of how these things work.
So you said it only works under a certain miles per hour, like only works under 8 miles per hour. Can you then spoof miles per hour?
Yeah, we never unfortunately got to figure out if we could spoof that it was going less than a certain miles an hour. Unfortunately, a lot of these tests was like we were coming up to DEF CON, the CFT was ending, and we're just like, let's get our milestones out, get this done. Then I wish we would go back and be more thorough, but I'm not going to lie to you, that's not going to happen because we're lazy. Firmware. How do we get the firmware? You can watch how things like the Ford IDS tool update, right? There was 3 updates that we could download for different things. The same with Toyota. It actually did, request download and transfer data and things like that after you did security access. Luckily, right, we figured out how to bypass the security access because we have all the keys. And then finally, you could do things like routine control. And think of this as RPC. You put code in memory and then call it and it runs. And they're designed this way. This isn't like, a hack. Dumping the firmware. For Ford, luckily, they were Freescale chips. What you do is you call Joe Grand, Kingpin, and you say, help me, Joe. I need help. And he'll tell you get one of these hardware debuggers. You set it up. And luckily, right, you could dump the firmware. It didn't have the security bit set where you could only erase and write. You could actually read off. So you literally just use the development environment, dump all the firmware off. We know the firmware and we know the chipset. Luckily, I'd already had a processor module for this Motorola chipset. And then again, Charlie and I are software engineers by trade. This is the good part. Like, man, I just want code. All the car stuff is super hard. Like, this is what we wanted to look at, figured out, based on the architecture, what areas of memory are used as buffers for CAN stuff, how do you do interrupts to send and receive messages and the such.
All your annotated function names, do stuff, send response.
Oh yeah, do long operation no call. Thorough investigators we are. You have cross-references to data sections. This corresponds to registers and stuff that hold CAN data. Switch statements, right? You could say if you know an ECU is looking for these IDs, you can potentially find some switch statements to do stuff. Request download, you see certain bytes. Request upload, you see certain bytes, things like that. We have a tool chain for all this for Fords for the HC12X. So if you want to write some SM code, write some shell code for Ford, Python scripts, basically you just have to write the shell code, run our script, and it'll dump it on the ECU for you. Why is this part important to us? We wanted continued access. If you're familiar with like PC security, you understand the concept of persistence, right? Not only do you want to infiltrate someone's network, you want to install your backdoor, your rootkit, whatever, so you maintain your persistent on the devices. So in this example, we do the most benign thing ever. We reflash some of the firmware to always think that the car is going in reverse, so the backup camera will be on. The reason we did that is because it's the most benign thing ever. The car will still function, it's not going to explode, but generally speaking, since this was a routine control, there's a portion of memory that we can just write to. The ECU still worked properly. We just had also our code.
Backup lights on them too?
What's that?
Your backup lights on the whole time?
No, just the camera. Just the camera. So this one, and here's how fast it works too. So here's Charlie reflashing. All right, our shell code is in the memory region. It's called, he pulled the plug on the closed test track. That's our lead truck to clear the way. Yeah. Yep.
To use a diagnostic routine control for that.
Yes, routine control.
That's why I know when the camera came up.
So the reason this is important, right, is not only can you send messages, you can write to ECUs. I'm sure if we did more work, we could write more persistent code on there that could reside there between runs and everything like that. But there's a capability for persistence is all we're saying. There is a capability to stay on the car after you've initially infiltrated as well. Or if you have limited physical access for 3 seconds, 4 seconds, you can do what you do. Toyota, it was much more difficult. Different chips. They were mainly Renaissance chips. They bought NEC, so V850s. Those were involved in the Camry unintended acceleration, same chip, and M16Cs. So the reflashing process didn't follow any of the standards. It was a proprietary reflashing. Luckily, I spent 2 months and I reverse engineered the whole protocol and wrote parsers and a reflashing script in Python. So if you want to do this, you can use my script to reflash. I went after the transmission control because I figured it was an M16C, which we could see there. That looks like debugging headers because you have a crystal here and your MCU. You could get a E8A Renaissance debugger. You couldn't hook it up. You had to do pinouts. And by you, I mean Joe Grand. Looks something like this. And normally, you would pull the firmware off in the same way. Toyota was a bit trickier. To pull the firmware off, you need a 7-byte password. It's normally default to all zeros or all Fs. Good job, Denso. It was not zeros or all Fs, and we actually couldn't get the firmware this way. Luckily, not for this one, which isn't in the slides. The updates, I figured out methods to derive firmware, not full firmware, but partial firmware from the updates. So as long as you have a mechanics account and know the architecture, you can use some IDER Pro and get yourself some firmware that way. But this way,
from like reinforcing that key space?
you have to reset. If it's 3 times, I think it locks. So you have to physically turn off the power and turn it back on. So you could do it, but it'd be a long time, aka forever. Yeah, it's possible. Honestly, if you have someone like Chris Tarnowski, you send it to him, right? He decaps it, not worrying about debugging headers, and you're going to pull the firmware off that way. I'm pretty confident that Tarnowski, if he would have done me a favor, would have done this for me. Reverse calibration files, I talked about that. Very viable. They're unencrypted. I also have a thing called CUW. That's the calibration update wizard for Toyota. CUW_fixer.py. That shows you how to do the whole format of the calibration updates, rip them apart, fix them, fix the checksum. So you can actually just alter those files and actually use the Toyota tool to update your custom firmware that you want to write. Detecting attacks. Here's where we try to do some good. Normal packets, like I said before, right? The speed happens, we'll say 10 times every 2 milliseconds. These frequencies are very predictable. It's not like the internet where you don't know what the traffic's going to look like. If you saw 1,000 speed packets in 1 millisecond or 10,000 in a second, that's obviously not what the car's doing. Someone's doing that. So you can detect attacks based off anomalies, especially frequency anomalies as well, right? Diagnostic attacks are easy. Basically, all the academics attacks and a lot of our attacks, especially the braking, while you're driving, you shouldn't see security access come along to the ABS ECU. That's just not how it should work. I mean, generally speaking, right? You don't want this to happen ever when the car's moving. So these things stick out like a sore thumb generally when you're doing them. And I think OnStar will send some of these, but you could probably account for that when trying to detect.
That's what I was wondering, like OnStar while you're...
Yeah, I mean, that's how they, when someone steals your car and you're like, yo, shut that shit down, they'll send a message, right? But I think if you were writing some kind of system to detect these, you would figure out what OnStar was sending and saying, generally these are probably cool.
There are legislation coming for tracking drivers.
Yeah.
But the things with those, like you said, you know the pattern. You can find the pattern. It's it's very periodic.
Exactly. Yeah, it's predictable. It's a really enclosed network, right? It's not. There's a reason anomaly detection doesn't work for internet traffic because it's so varying. But with these things, it's pretty standardized, and you know what to expect the entire time because you made the car. In your response, we talked with Ford about some improvements before we released. So we emailed both Ford and Toyota like several weeks before Black Hat or DEF CON, and just said, here's all of our work, and here's what we're going to publish, and here's what we want to do. We're totally up for helping to try to fix the problem. We had brief conversations with Ford. Toyota never bothered emailing us back. Still to this day, hasn't said a word. There was some canned pre-R statements that wasn't considered hacking because don't worry, they do external testing of their wireless networks. All secure, nothing bad, you're cool, forget about it. Don't worry about people like us. You can't take over a Toyota for sure. So I take that as if you can get a remote attack at a Toyota, they admit that you can completely wreck the car, right? Because they're only protecting external resources.
Just for reference, the Denso engineers I mentioned that eventually went on to Arbor Networks that are kind of close buddies. When I talked to them about like infotainment and the CAN bus,
yeah,
they're like, oh yeah, they're on the same bus. And I was like, are you serious? And they're like, what? What's wrong with that?
Bro, yeah. Well, it's one of those things, right? They live in an environment where security isn't key to them. It's pushed to market, and the last thing, and I understand the difficulty. I have talked to not Ford or Toyota a lot, but other automobile people, and it was like, listen, dude, they live. If you tell them like, hey, next Chevy Cobalt's going to be 6 months late, not acceptable. Like they're pushed to market is their whole deal. So it's hard for them to say, hey, do penetration testing or this or that. So I understand there is a business related to all the security stuff as well. But that's why I get to make brash statements like these. Conclusions. I think we proved that automobiles can be physically controlled over the CAN network. To some, that's shocking. To many, it's not. To me, it was really cool to figure all this stuff out. And that's really why we did all this stuff. If you compromise an ECU, generally speaking, there's not a lot of segmentation on automobile networks, at least as we speak. Compromising an infotainment system can lead into attacks that we showed today, right? We're just hoping that we lower the barrier of entry. People can start doing this work, and we can start having discussions with manufacturers about what we can all do to work together. This reminds me a lot of Microsoft in the 90s, where they just didn't want to talk to people, they didn't admit there were problems, but lo and behold, they realized that talking to researchers like Charlie and I is a good thing. We're not out to get them, we're out to do fun research and be media whores about it, and actually help them out in the long run, right? We want to help. It's not like I'm trying to jack them up all the time, just some of the time. If you're interested in this stuff, we have a 101-page white paper, documents not only our successes but our failures. So you can learn about where we messed up and things we went wrong. And I'm sure you could probably find places where we're incorrect. Read it, all the tools, all the data, everything we ever did, one big zip file, and it's out there. If you Google car hacking the content, it will be the first link, and get all that stuff. So greets, Joe Grand, he's a man for sure. I don't know, I can't speak more highly of anyone than Joe Grand. Maybe John O. Maybe John O can be spoken of as highly. Stefan Savage, he's the guy who ran the academic research labs. He actually had lunch with us in San Francisco and discussed what we were doing, and we talked through some things. And of course, Mudge, he's the one that hooked us up with the Cyber Fast Track, got us these cars, let us have a bunch of fun for 9 months. So can't thank them enough. If there's any questions, you can follow me on Twitter, email me. I'm always doing interactive stuff. Just wanted to thank Duo and John O for having me here again and setting this all up. This is awesome. Thanks a lot for coming. I appreciate it. That's it.